Welcome. In the last lecture, we had studied about two interesting architectures, and they were much deeper, and you could go up to hundreds or 200s of layers over there. One of them was residual network. The other one is what is called as a dense net, or a residually connected networks over there. So today we are going to do hands-on for the first variant of it, which is called as ResNet, or a very deep network with a residual connection over there. Now, it's not much of a change as far as the first part of it is concerned, and these are also some things which take good amount of time. So I am just going to show down a notebook which has most of the things which are recompiled over there, and we do a simple walkthrough of it. Now, over here the first part is pretty simple, which is your just the header files or the initial ones which you need to take in, and then next comes down your data over there. Now, this particular network quite different from your unlike your Google Net, which would have needed you to take down 209 cross 229 sized images over there. So here we take down smaller ones which are 224 cross 224, and this is a network which has been trained to stick down exactly to my ImageNet kind of models and ImageNet kind of sizes. Okay. Now, here fortunately we could take down a larger batch size, and that's all dependent on how much of intermediate data my model is handling. So based on and then that's a pretty easy calculation based on what we had done in the earlier lecture itself. Now, you need to work it out around over there based on how much your available RAM is there. So while in Google Net we had to stick down to a much smaller batch size of 32 based on the particular card I was using over here. So for me, with this given with the same card and the same kind of a system architecture, I am able to get down more number of images, and here I am pretty convenient taking down 128 images into one single batch. Now, the rest part is quite simple. So instead of doing it with ImageNet, we are doing with a smaller data set called a CFAR, and this is just a 10 class classification problem. Now, based on this 10 class classification problem, accordingly we will also be modifying the network architecture which we download from our model zoo available with us. Now, that's this for this first part of it, which is quite straightforward and clear. There is nothing much to do. Now, the next is to look into whether the data has been loaded down, and yes, the same way that we had divided 50,000 for our training set and then 10,000 for our testing set, the same thing comes out. So that's pretty straightforward. Now, here what we do after that is we just get down our models, and this is my ResNet 18. So this residual network is just 18 layers deep, and I am choosing down only a very smaller one. You can go down to 151 layers as well, pretty much, but then you need to keep one thing in mind, that your batch size will reduce and you will take much longer time to finish off each of these epochs. Now, in order to avoid any of those problems over there, I am just using a smaller model over here, and this is just residual network 18. Now, there is also another fact that I am not trying to discriminate between multiple number of classes. So in the earlier residual network, which was really deep, that is something which was done to actually classify between 1000 classes of objects over there. Now, I am choosing down a very smaller one, which is just 10 classes of objects, and now just because of using 10 classes of objects, I can have this liberty to actually go and choose down a much smaller size network. Now, that is what I am doing with choosing down ResNet 18, and this is what you can look down on the whole thing. Now, over here we do not make actually much of a change to the whole network, and you do not have any issues of an auxiliary arm or something coming down over there. Now, what does definitely come to play is that all of your basic blocks and everything being put down together. The next interesting part is that your final one is something which gets down 512 as a linearized feature vectors at the terminal layer, and then this 512 are what are connected down as a fully connected network onto 1000 layers. Now, this is the part which we need to modify, because we did choose that we would be going down with just a 10 class classification problem and not a 1000 class classification problem. So this is the only change which comes down, and quite unlike the Google Net, which we had done in the earlier session, is where you had these auxiliary arms. So you also had to modify the auxiliary arm. You do not have this issue over here because there is nothing of an auxiliary arm. But given that, the main point which comes down is that you have these residual connections as well. Now, and just by virtue of these residual connections which are present over there, so your gradient is actually backpropagating much easily, and because of this easy backpropagation of the gradient, we do not need to worry about whether there would be a vanishing gradient at some point of time as we are traversing down the depth over there. Now, That's pretty much simple and easily done. What you need to keep in mind is that because of these residual connections, it's again made down in the same kind of a tabular form of connecting. So you first build up the small blocks over there for each of them, and then you drop down residual connection and keep on doing a parallel connection and build it up. So this is quite similar to how you were doing it down for your Google nets. Now since we are not doing much on the data structure of these neural networks as such to do so, and that's pretty much well documented within PyTorch community's documentation, so I will not be spending much of time over there. But my most important factors to discuss are more of related to what happens within the learning dynamics, what you need to make a change from adapting a model from an existing one to your particular one, and further on as we keep on going over there, and what are the properties which does come to impact. Now once that is done, we look into the total number of parameters, and then if I go through them, you would see that as a total calculation, this particular model is something which has 11 million parameters over there. Now this is definitely a model which is almost the same size as in a Google net, but it does have much lesser number of parameters, and by virtue of a lesser number of parameters, you have a model which takes lesser space to load. By virtue of lesser number of parameters, your intermediate operating points also consume lesser amount of memory. That's something which we had done for one of our networks earlier. Now just because of this sheer interesting aspect and attribute present down within the model, you can now actually feed down much larger batch sizes. Now one thing you know is that if you are feeding down much larger batch sizes, then the total number of back propagations over there is obviously decreasing, and once you keep on decreasing the number of back propagations, so your compute is definitely going to become faster and faster over there. So one is the compute which is steady, which is for the forward pass, and that is dependent on the order of the sample size within your training set over there. But then your back prop is always dependent on your batch size. So larger the batch size, the lesser number of larger is the batch size, the lesser is the number of batches which fix in over there. So the lesser is the number of back propagations you are going to do, and that's something which does definitely come to play a very important role. Now here this is what we have gone down and looked down. So this particular network has about 11.7 million parameters. So when we had in the earlier theory, when we were comparing down our ResNet versus DenseNet, and there was one of these plots which was plotting down the total number of parameters versus what is the accuracy, saturation accuracy achieved over there. So you did see that DenseNets for the same kind of a depth have almost half the number of parameters to come down to the same kind of an accuracy over there. So this is something which we will do in the next class when we compare down with DenseNet and do a practical hands-on with DenseNet, is when we get down the parameter calculation over there as well. Now the thing which you need to modify for this network is your last layer, which is the FC. Now if we go over here, this is my FC layer, and this FC layer has to be changed from this kind of a linear structure to something which connects 512 to just 10 nodes over there and nothing more than that. So that's the change which we bring over here. So it's a linear connection from 512 to just 10 nodes, and that's the modification which we do for residual network to be used for a CFAR 10 class classification problem. Now once having done that, the next part is just to copy down all of my weights and keep it. So these are my initial weights. Now I will look down what happens after my whole training. The next is pretty straightforward and simple, as we had done in the earlier case, is to check down whether I have a GPU available with me and whether CUDA libraries and resources are all set and running. Now if I have that, then I can just keep on using my CUDA for acceleration. Now once that is done, next is to look into my criteria. It stays the same as in for classification. We choose to stick down with negative log likelihood classification criteria, and then with Adam as my optimizer. Now in the earlier classes we had discussed about different kinds of optimizers and their features and the different attributes which they play down, and what we did figure out that adaptive momentum and also via experiment we have seen down that adaptive momentum under general operating conditions is something which would take a tad bit longer to actually optimize and give me the results, but then it's something which would definitely guarantee convergence at much lesser number of epochs, as well as if you take the total time consumed. So your per epoch time is increasing because your per batch time is increasing on view of the Adam optimizer over there. However, this net product of total number of epochs into the time taken per epoch, that is much lesser when it comes down to Adam in order to come down to a saturation point. So that's definitely interesting, because in terms of how many minutes or hours or normal human time and CPU time it consumes, that is being brought down significantly by use of Adam. Now once this part is done, next is to look into the network and we start training the network. So, here what we do is go down with the same plain old rule of training it down just for 10 epochs. I do not range it more than 10 epochs, it does not play a role over here. And then although this does not take much amount of time, this network does train much faster than GoogleNet, which otherwise would have taken down about 8 minutes, close to 8 minutes to do it. So, here it goes down about barely between 1 and 2 minutes over there. Now, within each of my epoch, now the difference which comes in, that here this is just one single tapped out network, which means that the classification and the losses which you get down is only at the end part of the network, it is no more in between. So, in GoogleNet you had these auxiliary arms coming down, and for that reason you also had to get down the losses computed out of your auxiliary arm, and you also had needed to do a back propagation with the losses being fed down over there. Now, we do not need to do any of those for our case over here. Now, here what you are just going to do is plain simple calculate out the final loss over there, and then do the back prop. Now, within each of these batches which comes down over there, you for zero down your optimizers, gradients and everything, and then you convert your if there is a GPU available, then you convert your variables into GPU and then typecast it as a variable, so that you can do your back propagation operations over there. Next is you find your feed forward and get your output, then you find out what's your predicted and whether your predicted is correct or not, and then this would help you in getting down your error over here. Okay. Now, once I have all of this done and my errors computed and then done, then what I do is I do a back propagation of my loss over there, and the optimizer comes into play in steps. So, whenever I do a step, it means that the optimizer is being solved over there and my weights are getting updated. So, this is where my weight update happens, and then I have my running losses which are just calculated and stored. Now, within each each epoch over there, I am passing down all my training samples, and I have in total 50,000 training samples over there. So, if I need to find out my accuracy or my loss, then I will have to take some sort of a average over there, and that is what I am actually doing over there. Now, once that is done, then train ACC and train loss, these are the two different arrays which are just being created dynamically. So, one array has an entry for each epoch over there. Now, once that is done, the next part is where we need to get down next part of it is running, which is my validation over there. Now, in validation, what we need to keep down in mind is that one point which we set down over here is false. We just give an identifier that we are no more training the network, and this is for the reason so that your batch normalization does not come into play. So, typically when you are training a network, you will always be trying to normalize in batch. So, whenever you have a batch norm coming to play, so there is a batch normalization taking place. But whenever you are doing a feed forward and just an inferencing over there, your batch sizes may be different, and based on that it will have a different dynamics coming out. So, the same sample, if it is located at different batches based on what all other samples are located in the batches, if the other samples in the batch are changing, then the whole thing gets normalized along a batch, and the response has a very skewed out behavior. So, in typically during inferencing we do not use batch normalization, and that is just switched off. So, this is a very simple way of actually switching off all of my batch normalization issues. Okay. Next, what I do is just find out if my GPU is available, then I typecast my data onto a GPU CUDA array, such that it resides on my GPU memory and my network can also work on my GPU, and then I find out my outputs, do a prediction over there, and then find out whether it is correct or not. Now, that is what you would be doing down for your feed forward on the validation side of it, and then since there are 10,000 samples present in my validation which get evaluated every epoch, so I take an average over all the 10,000 samples. The next part is pretty simple to plot it down, and there is nothing much of a change. Now, if you look down at how the model was working out, so we trained it over 10 epochs. It takes about 1 minute 51 seconds. So, that is about 8 to 9 seconds short of 2 minutes is what it takes down to train it down. Now, it starts with an average accuracy during training for testing somewhere at 50%, and then my test accuracy goes up to something around 70%. Now, in between it was at 75%, 73% as well. Now, you would see that my training loss is what is starting at 0.1, and then it keeps on going down and down. Now, while my accuracy had gone high on my testing side, so you see that it goes up to 71%, then falls down to 55%, then again goes to 71%, then to 67%, then again to 75%. But on the other side of it, you would see my training loss is constantly decreasing. Now, one thing is there are few people who would argue over here that possibly I am overfitting on my training loss, and that's my testing one is going down. But nonetheless, you need to keep one thing in mind, that this kind of a jitter behavior over here is something which is happening because it's possibly hopping from one minima point to the other minima point. Now, that's the beauty of Adam which comes to play over here, that you are not getting locked into local minima points, but then you can hop and you're going down towards a global minima, and that's the dynamic change which you are observing over here. So 10 epochs get in total of 18 minutes and 38 seconds. So that's roughly about 1.8 minute per epoch, and that's not so bad actually, given the fact that when we were trying to do it with GoogleNet, it was actually taking me about 8 epochs, 8 minutes per epoch, and here I am something about 2 minutes per epoch. Now I have a model which is roughly 1/3 of the model size, but much deeper, and it takes me about 1/4 of the time to run it over here. Now that's a total cumulative thing which comes down. So if you can really play around with your architectures, you do save a lot of your resources over there. Now we have our train and test losses over there. So you would see that your training losses is something which starts lower and keeps on going, and your test loss is still going lower, but it does have a jittery behavior. On the accuracy side of it, you see this whole jittery behavior between 51% and 71%, and keeps on going. So somewhere around at the end of 10th epoch is where it sticks down to 70%, and that's more or less where it will be sticking down, because you can see that it's almost over there. It's roughly at 70% where it keeps on going. So you can keep on training over a longer number of iterations, which I would typically suggest you to do, and find out where it keeps on saturating. The next part after training is to copy down my weights and then try to look into the visualization of the weights over there. That's what we do over here. Now if you recall from the discussions which we had on the architecture, so the first layer over there is something which has spatial kernels which are of span of 7×7, and that's what we plot down over here. And there are 1 2 3 4 5 6 7 8 and 1 2 3 4 5 6 7 8. So it's a 64×64, and if you remember from your earlier lecture, you can actually flip back onto that earlier one. So you had these connections from 3×2 to 4×2 to 4, and then you had 7×7 kernels, and you had 64 of those. So each is one of these kernels of 3×7×7. 3 is for the input number of channels, and then you have 64 such channels which are visualized on a 8×8 grid of these kernels coming down. Now these are the weights at the initial, which is at randomized start over there, and then these are the weights which come down after 10 iterations of training. Now if you look down at the difference, yes, there is a significant amount of difference, you see, and these are more of like gradient based changes which come down. Although like looking down at the kernel, it's really hard to understand like what is changing over there, because they still appear as random pixels of color. Now here you would be seeing that there are certain kind of directional gradients which start setting in over there, and these are more of color based directional gradients. Now that's an interesting factor which does come into play, and but then given the fact that we are not putting down any imposition on what is the nature of change which should take place and how it should be taking place, the only thing which we are doing is backpropagating my gradient across the network over there. So that's what happens, and it keeps on changing. Nonetheless, to say that since this is a residual network which with a much wider receptive field on the first layer over there, so you are able to encapsulate much wider aspects of the images and the objects present in those images, and that's what does play a significant role. Now CFAR, which was a much smaller 32×32 or 64×64 things which were scaled up to almost 8 times of that, to 224×224. Now instead of that, if you are taking down very detailed images of 224×224 on which are available on your ImageNet, so that's something which we will leave down to all of you guys to do. It's a large data set, you need time to download. You would also incur more time to actually train down per epoch as well. Now if you are able to download that and do over there, you would see that there would be much finer granules of changes which would come down, despite it would also be needing down more number of epochs. So that's something which I leave up to you. You are free to do. So you can in fact look into any of our other data sets which we had done with autoencoders and stuff as well. You would be getting down a very different behavior for each of them, and that's something interesting to really keep on looking down over there. So that's what we have for the first convolution kernel over there. Next, if we look into the next kernel, which the next layers are now 3×3, the first layer over there, and then this is one of these kernels, and now since it connects all the 64 over there, so you still have one layer which corresponds to one of these convolution So for one kernel, you have 64 such channels which are over there, and each has a spatial span of 3 cross 3, which connects on the previous layer. And since the previous layer is giving you an output which has 64 channels, so here also you need to have those many 64 channels, and that's what you get down. So these are the initial weights before training, these are the ones after 10 epochs of training, and this is the kind of changes which happens. And now these changes are really massive, these are not zero changes, these are all non-zero changes. Now this is another thing you need to keep in mind. Now a very higher difference comes down when trying to compare it with Google Net. Over there wasn't much of a change in majority of them in the second layer coming down, but here you do see a change coming down over there. Now that's interesting to explore out as you keep on going down. Now that makes me come to an end for residual networks, and then stay tuned for the next lecture, where we would be doing and discussing about what happens with densely connected residual networks or dense nets. Till then, thanks.